Okay, so today, what we're going to do in today's lecture and part of the lecture on Monday is we're going to look at graphical models. The reason why we need to look at, how many of you had experience with graphical models? How many of you taken a graphical models class? Okay, so for some of you, this is going to be just a repetition, but there aren't that many. But we need to cover graphical models because we're going to start looking at Boltzmann machines, variational autoencoders, deep belief networks, and all of these models are rooted into graphical models. Okay? So we will need to have a pretty good understanding. And for those of you who haven't taken graphical models class, this will be like a very quick pass over the directed and undirected graphical models, and you should be familiar with all of those models, right? Because later on we're going to start looking at more complex graphical models, and the basics you should know. Okay, so graphical models. These are probabilistic models that essentially modeling dependencies, introducing dependency structures between random variables. So graphical models have certain properties, certain useful properties. They typically provide a simple way to visualize the structure of the probabilistic model that we're working with, and also a way of motivating new models. What you will see when we start looking at the landscape of deep generative models or deep learning graphical models, you'll see a lot of different models kind of look similar from graphical model standpoint, except for they'll have very different properties. So you'll be able to see what's the connection between variational autoencoders and Boltzmann machines versus deep belief networks and deep Boltzmann machines and such. They also provide various insights into the properties of the model, particularly looking at conditional independence. Conditional independence properties that will form the key for us to design inference and learning algorithms. And typically complex computations, such as inference and learning in these models, can be expressed in terms of graphical manipulations, right? To that point, there's been a lot of work in IT sector where people were trying to write up engines that you can specify your model, your graphical model, and you run the inference algorithm automatically compiled on the graph. So based on your graph representation, you have a compilation of the model and can do inference and learning. So what is a graphical model? Well, it contains a set of nodes, vertices, connected by links, edges. Okay? So it's a bunch of vertices and a bunch of edges. In the probabilistic graphical model, each node here would represent a random variable. So here we have random variables x1, x2, x3, x4. And links between these variables would represent probabilistic dependencies between these random variables, right? So which variables depend on which other variables. So the graph also specifies how the joint distribution over all of these random variables decomposes into the product, particularly decomposes into the product of factors, where each factor will depend on a subset of the variables, okay? So it will have a very specific semantic structure. There are two types of graphical models. One type is known as Bayesian networks, or sometimes also called directed graphical models. And in these particular models, you have links that have particular directionality indicated by the arrows, right? So it's a directed graph. So if you've heard about things like Helmholtz machines or variational autoencoders, all of these are instances of directed graphical models. And we'll see that, or instances of Bayesian networks. And then there's another class of models known as Markov random fields. These also known as undirected graphical models. So in this case, links don't carry any arrows, and there is no directional significance. Okay? So things like restricted Boltzmann machines are instances of undirected graphical models. And then there are also a combination of both of them. These are hybrid graphical models where you have both directed and undirected components. So for example, deep belief network is an instance of a hybrid graphical model. We'll look at these examples later in the class. It's very difficult to combine both of these models. You have to be very careful when you're combining them because they carry very different semantic meanings. So let's look at the Bayesian networks first, or directed graphs. So directed graphs are usually useful for expressing causal relationship between random variables, right? So particularly, let's look at the joint distribution of 3 random variables. Okay? Now, we don't need to specify anything about our random variables, whether they're discrete or continuous, but simply by using the product rule of probability, I can always write down this joint distribution into this form, right? I can say it's conditional probability of C given AB times the joint AB, or again, I can apply the rule of product rule of probability and can say, well, it's a conditional times probability of B given A times P of A, right? For any probabilistic joint distribution, I can always write it down this way. Okay? Yeah, so this is decomposition for any choice of the joint distribution. Now, what I can do is I can specify a graph corresponding to this particular decomposition, right? So I can represent the joint distribution in terms of simple graphical model has this form, right? So what you do is you introduce a node for each of the random variables. You associate each node with its corresponding conditional probability. And then for each conditional distribution, you add a directed link. So let's look at the graph itself. I have prior probability P of A. That's P of A. There are no incoming links. Then I have probability of B given A, right? So it's conditional probability of B given A. So that's a directed link here. And then I have a conditional probability of C given A and B. So here I have conditional probability of C given A and B, right? So you can see the links coming over. So the factor, this conditional factor, there are going to be links from nodes A and B coming to node C. So it basically says this conditional probability really depends on the states of A and B. Okay? And the factor of P of A doesn't have, there are no incoming links. Okay? Now, if there is a link going from node A to node B, then we're going to say that A is a parent of node B. Okay? So obviously it makes sense, and node B is a child of node A. So typically when people talk about Bayesian networks or directed graphical models, you can say what are your parents and what are the children. And that's going to be important for us when we're going to start defining inference algorithms, learning algorithms for these models. Now, for the decomposition, we choose a specific ordering, right? This is a specific ordering that we've chosen. We first started with A, and then look at conditional probability of B given A, and conditional probability of C given A and B, right? If we choose a different ordering, we would get a different graphical representation, right? So we'll come to that point a little bit later in the class, but that's something to be aware of. So the joint distribution, another thing is that if we have k random variables, think of, when we work with large-scale models, k could be on the order of thousands. There's going to be thousands of variables. Then again, the joint distribution can always be written in this form, right? The conditional form. If each node has incoming links from all lower numbered nodes, then the graph is fully connected. So you basically have a link between all pairs of nodes, right? So obviously, if I look at any joint distribution, and I have that particular structure, then the graph is known as fully connected. But if we have a graph, there's certain links are missing, absence of certain links conveys certain information about properties of the class of the distributions that the graph conveys, right? So when the links are missing in the graph, it tells us something about what kind of distribution we're looking at. So for example, this graph is not fully connected, right? There is no link from x1 to x2. So the joint distribution over x1 and x7 over these random variables is a product of the set of the conditional distributions. If you actually look at this graph, you can think of it, this is layer 3, this is layer 2, this is layer 1. Right? And we'll come back to this point later on in the class where we're going to be constructing these layered graphical models, right? But what's interesting about this one is if I look at the joint distribution over all of these random variables, I have this particular property, right? So let's look at this particular property. What am I saying? Well, I'm saying there's P of x1, P of x2, P of x3. So these random variables are independent. Right? I specify the prior probability for those. Then if I want to specify P of x4, P of x4 depends on x1, x2, and x3, but x5 only depends on x1 and x3. Right? So you have links missing here. Right? So I can read from this particular graphical model what's the joint distribution and how it factorizes into these conditional distributions. Okay? So the joint distribution defined by the graph is given by a product of conditional distributions for each node conditioned on its parents. So it's always I'm looking at the node and I'm conditioning on my parents. Right? So now I can specify the joint distribution over all of these random variables as a bunch of these conditionals. P sub k denotes a set of parents for node x sub k. Right? So this is fairly straightforward. And this particular equation, expresses a key factorization property of the joint distributions for directed graphical models. Right? So this is really telling you how the joint distribution factorizes into these conditionals. Okay? So there is one important restriction for these models, is that there must be no directed cycles in this graph. So for example, I can't add a directed link from x7 to x3, because that will introduce a cycle. Question is why? Why do you think that's not allowed? Or that's not a good idea?
Does the cycle indicate some sort of feedback in the system? Like one variable depends on other and the other depends?
Sure, it could indicate some kind of a feedback, but then the question is, what can go wrong? Like, why can't I just add cycles and just represent, just multiply a whole bunch of these conditional probabilities? Yeah?
Well, because if because for the variables, it might overflow.
Overflow.
Yeah. Because they're affecting each other's, like they're reinforcing each other's.
Sure, but why not? They can just keep reinforcing each other. What's the problem with that? No, it's like a recurrent network. Yes?
The factorization will be endless. It will be decomposed as
The factorization will be endless, but that's maybe I can just write it in as a geometric series or something like that. Why not?
they are not independent to each other anymore.
They're not independent of each other, but why is that a problem? They could be dependent. Any guesses? Yes?
Prior is also the posterior.
Prior is also the posterior. Sure.
The overall probability might die down to 0.
The what?
The overall probability might go down to 0.
Sure. But why is it the problem? Yes?
It's not going to satisfy the properties of probabilities.
Exactly. So what, like if I add the edge here, there might not exist a joint distribution that's a valid probability distribution. Right? Think of it this way. If I give you conditional, like if I give you two nodes and I specify conditionals, like I specify the conditional, let's say I have two nodes, A and B, and I specify the conditional probability of A given B, and then I specify the conditional probability of B given A. So I have link this way and I have link this way. There is not necessarily guarantee that there is a valid joint distribution, well-defined joint distribution over those random variables. So it's not like I can just multiply a whole bunch of conditionals and somehow magically the joint distribution comes up. The joint distribution might not be consistent, right? The only way I can specify is if I specify the joint distribution and then I can derive a bunch of conditionals from it. So if I start adding edges, there is no guarantee that this probability distribution is going to be a valid probability distribution. Okay? And so that's why we cannot have cycles in this particular model, right? Because it might not correspond to a valid probability distribution. So these graphs are generally called as directed acyclic graphs, DAGs. Let me show you one example of a DAG. We haven't looked at the Bayesian models, But what I'd like to do is I'd like to show you Bayesian polynomial regression. And just sort of we can go over this particular example. So we've looked at this example before, right? You're given some inputs, you have some targets, right? Your inputs are these blue points. No, your inputs are your axis, and your targets are, these blue points, these targets that you're trying to predict, right? Given the prior of the parameters, the joint distribution can be written this way. So in Bayesian framework, you can always say, well, these are my targets that I'm trying to predict. That's my prediction model. Could be a neural network. And this is the prior over the parameters. So if I want to specify the joint distribution, I can write down the joint distribution. So this is sometimes known as the prior term, and then this is known as the likelihood term. But I can specify the joint. How can I represent it graphically? Well, the distribution can be represented as a graphical model this way, right? Why can it be represented this way? Well, I have prior over the parameters, and then I have a likelihood term. And these likelihood terms independent of each other, given my W's, right? Because it's a product over all of these n data points. So that's a graphical model. You can also sometimes people use plate notations. Not so frequently in today's literature, but if you look at papers, 10 years ago, people would also use plate notation like this. You're just repeating it n times, basically. And that's just a compact representation where you're introducing this notion of a plate, and then you're just basically saying, well, this node is going to be replicated n times. Okay? Note that in this case, W, the parameters, represent random variables, and the targets that you're trying to predict are also random variables, right? Because that's how you're specifying. Anytime you're specifying a distribution over something, that something is usually a random variable, right? You can think of it that way. It will also be useful to make parameters of the model as well as random variables be explicit. So for example, I can say, this prior term here depends on some other parameter alpha. And alpha is your hyperparameter. Right? Think like a variance, for example, parameter. In this case, I also have some variance parameter hidden in my likelihood term. That's my variance parameter, and then I can kind of like specify, make an axis or condition. I'm always conditioning on axis. And these are random variables, and this is what you condition on. So you can say the prior could be a Gaussian prior, which is in Bayesian models. You typically have some model. You can say, well, the prior with the parameters could be a Gaussian prior with some variance. And then the likelihood term itself is a Gaussian distributed with some variance, but where the mean is given by m degree polynomial. Right? So that would be one example of where you do Bayesian curve fitting. So in this case, random variables are typically going to be denoted by open circles, and the parameters are going to be denoted by smaller solid circles. And generally, when you read some papers, sometimes people use that notation. Sometimes people drop dependencies on these things and just show the random variables and show what's connected to what, but nonetheless. So if we want to apply the graphical model to a problem in machine learning, basically the idea is that what happens is some of these random variables, we're going to be fixing them to specific observed values, right? So think of, for example, training Bayesian regression on the data. You get to observe targets, right? And if you get to observe targets, these targets are observed. And maybe you want to figure out what's the posterior distribution over the parameters. Or if you're interested in map estimation, that comes down to doing least square estimation, right? To find what these parameters are. So in many cases, when we're going to look at graphical models, we're going to have a bunch of random variables that are unobserved. These are our latent variables. And then we're going to have some variables that are observed, which is our data or our targets. What is it that we're observing? And the role of the inference is to figure out the states of unobserved variables, is also learn all the parameters. So for example, having observed the values of the targets on the training data, we wish to infer the posterior distribution over the parameter vector W. Right? So generally, that's what we're going to do. So we're conditioning unobserved data, and we're trying to figure out what the distribution over these parameters W should be, right? Now, in Bayesian statistics, there's something that's called predictive distribution, which is to say, how do I make predictions for a new data value X star? So I want to make a prediction for the new X star. If I want to make a prediction for the new X star, in Bayesian framework, you basically have to integrate out uncertain, unknown parameters and then make a prediction. Okay? So in this case, again, I don't want to get too much into Bayesian framework because that's not the goal of this class, but I wanted to show you that typically you can write down again the graphical model representation. You can say, I want to make a prediction for this by integrating this. So it's a joint distribution over the observed targets, the random variables, and you want to integrate out these random variables in order to make a prediction for this one. Okay? And the joint distribution is given by, in this particular example, it's going to give like, here's your likelihood term, this is the prior term, and this is the predictive term. So here you get, again, you're setting the random variables in T to specific values in observed data, right? So at the high level, you observe some data, you clump, and this is always observed. You try to infer some posterior distribution over the latent variables, over the parameters if you're in Bayesian framework. And based on that, you start making predictions. Okay? Now, when we start looking at these models, and these are very simple models, right? So here you can see there's only a couple of random variables. We're going to start looking at models where we're going to have thousands of random variables, right? So scaling inference algorithms is going to be, quite important. Let's look at how we can sample from these models, right? In fact, if you've seen kind of some examples of variational autoencoders or GANs, something that we're going to look at later in this class, sometimes people say, hey, look at the pretty faces that I can generate, right? Or look at the pretty images I can generate. How do you generate? For these kinds of models, you could generate using ancestral sampling. So let's say you have a joint distribution of k random variables, right? I specify this joint distribution. I specify the priors, all the conditionals, right? So I actually know what this form is. So we want to be able to draw samples from this distribution. How would you do that? Well, in this case, it's actually pretty easy. You start at the top, you sample in order. So you first sample P of x1 from its distribution. You sample x2 from its distribution, x3 from its distribution. Then you sample x4 from its conditional, but where you're clamping these conditional values to these sampled values, right? So the parent variables are set to the sampled values already, right? And then you sample x5 and so forth. The interesting thing about these directed graphical models is that if I want to get a sample from the marginal distribution x2 and x5, for example, I want to be able to say what's the marginal distribution, samples from this marginal distribution. Then what we can do is we can sample from the full joint distribution and just retain these values. And those values are going to be samples from the marginal distribution. That's the nice thing about directed graphical models, because sampling is easy. You just sample from the full system, and you retain samples that values of the random variables that you need to retain, and say that's a sample from the marginal. So when I draw faces from generative model on these kinds of graphs in variational autoencoders, on Helmholtz machines, when I draw samples, I instantiate my priors, I instantiate conditionals, and then I draw my data, and I just retain my data, sample data, and that sample is going to be sampled from the marginal distribution, which is exactly what you want. Okay? Now, generative models are typically, when we think about these kinds of models, it's Bayesian networks, directed graphical models, we typically think of high-level nodes carrying some latent or hidden structure. And the primary role of these latent variables is to come up with more complex distributions by constructing them out of simpler ones, right? You want to construct sort of complex distributions from a simple, typically exponential family conditional distributions. So conditional distributions could be simple distributions, right? It could be member of exponential family, but when you combine all of them together, you can have a very complex distribution that you're trying to model. So for example, you can think of generative model of an image. You have object ID, you have position, you have orientation, right? And then you're combining all three of them to get the image. So for example, you have object identity, position, or orientation, and they have independent priors. So a priori, you can say any object can appear anywhere at any orientation, right? So the image has the probability distribution that depends on these object identity, position, and prior, and this will be the likelihood term. So if I want to specify the joint distribution over all of these random variables, I can say, well, there is a likelihood term, which is what's the distribution of an image, or pixels in the image, conditioned on object's position orientation, times the prior terms, right? So that would specify sort of the causal process. So this particular graphical model captures the causal process where observed data was generated, and so the name is generative model. So these models are called generative because you can actually specify the distribution. You can sample from the model, and you have a distribution over the images, or pixel intensities, for example. This is very different from discriminative models, like a neural net style models, where given the image, we just try to classify, what class it belongs to, what orientation it is, or what object identity it is, right? So here it really is the generative process that captures the generative model. Now, one of the questions here, if you think about what do you do, how do you inference in this model? The idea is to invert the process, right? The idea is to say, well, in reality, what I have is I have images. I give you an image, and I want you to tell me what is the object in the image, what's its position, and what's its orientation, right? That's generally known as an inference task, right? So I give you an image, and you tell me what these values are, right? So we'll need to compute some form of posterior distribution that given the image, what's the distribution of object identities or positions or orientation, right? And this is what we will see known as the inference process. We have a generative model that instantiates latent variables, generates you the data, and then there is an inference process, which is given the data, tell me the states of the latent variables, right? So we will see that. Any questions about this? Okay, let's look at one particular example of discrete random variables. Very simple one, so I'll go through it very quickly. Suppose we have two discrete random variables, x1 and x2, each of which has k states, right? Then I can specify the joint distribution this way, right? If each has k states, then there are k squared parameters, right, to specify the joint distribution. So remember one of k encoding scheme, we're going to be denoting the probability of observing the first value taking kth value and the second value taking lth value by 1. And so this parameter mu kl is just the probability that the first random variable takes value k and the second random variable takes value l, right, and so forth. So this distribution is governed by k squared parameters, minus 1 because they have to sum up to 1. So in language modeling tasks, if you think about modeling bigrams, if at one point I have possibly 10,000 words, the second, I can have 10,000 words, what's the distribution that I can characterize? Well, that distribution is going to have, 10,000 to the power of 2, right? That would be the space of all possible combinations. And bigram models in language, which are very useful, are essentially trying to fit these k squared parameters, right? In fact, I believe Google can do 5-gram models where k is, on the order of hundreds of thousands. And 5-gram models are extremely difficult to beat, right? Because you have 5 distribution of all possible combinations of 5 different words. Obviously, a lot of them will have 0 probability, or very small probability, because they don't frequently occur. In fact, most of them are going to be 0, so it could be very sparse. But nonetheless, so you have k-squared parameters. So if I have a joint distribution over m random variables, and I want to specify any arbitrary distribution, then I'm going to have to specify k to the m parameters. And that will correspond to a fully connected graph. Right? Obviously, you can see exponential dependence here, which is really bad. Right? So it grows exponentially in number of parameters. Now, in this particular case, I have k-squared parameters. It's a fully connected. But if I have independent distribution, then I just have to specify 2 times k minus 1 number of parameters. Right? I just specify distribution for this one, and they could be completely independent. Right? So in one case, you have fully connected graph. In another case, you have fully independent graph. So you're dropping the link between the nodes, so each variable described is a separate multinomial distribution, right? So you have 2 multinomial distributions, you only have to fit k parameters. In general, if you have a fully connected graph, you have completely general distribution, and you have exponential number of parameters. So these are too complex to fit. Obviously, they are, you can model whatever distribution you want. If there are no links, the joint distribution fully factorizes into the product of the marginals, right? You can make them all be independent. It has only m times k on the order of mk parameters, right? You have m random variables. Each random variable has k parameters. M times k parameters you have to fit, right? We'll see later on when we start looking at variational inference for these graphical models in deep models. This will often be the assumption that we're going to be making. What if our models are fully factorized? Okay, so we'll come back to that point. Graphs that have an intermediate level of connectivity basically allows for more general distributions compared to the fully factorized one, while requiring fewer parameters than the general joint distribution. So generally, you will see models that we're going to be building by incorporating some kind of structure into the model, even just to reduce the number of parameters that we need to fit. So let's look at an example of the chain graph. Okay, so let's consider an m-node Markov chain. So Markov chains are going to be our friends when we're going to be doing inference in these models, right? But let's say I have a Markov chain expressed in this way. If I look at the marginal distribution here, p of x, it requires k parameters, k minus 1 parameters, right? Because it's a multinomial over k values. The remaining conditional distributions, p of xi given x minus 1, will require on the order of k squared parameters. In fact, if you worked with hidden Markov models, for example, right, you know that when you fit a transition matrix, if you have k states and k states, your transition matrix is going to be a matrix of size k by k, right? And if you want to make it symmetric or whatnot, you can you can reduce the number of parameters, but roughly you need to fit of order k squared parameters. So the total number of parameters is just going to be quadratic in k and linear in m. That's important. And this graphical model basically forms the basis of a simple hidden Markov model. If you haven't, we're not going to be covering hidden Markov models. We're going to look at recurrent neural networks. But if you haven't seen HMMs, hidden Markov models, I would encourage you to look at HMM. It's one of the basic, it's kind of like PCA of machine learning. You should be familiar with HMM. It's a very standard basic model for modeling time series data. The other thing that we can do is we can add priors, or we can turn the graph of a discrete random variables into Bayesian model. So by introducing Dirichlet priors over the parameters. This is another common thing that people are doing. So for example, from a graphical standpoint, we can specify it this way. Here's our Markov chain, and we can put the priors over every single random variable, right? Because this random variable will have parameters, and we can put the prior over those parameters, right? That's generally what you would do in Bayesian models. You can say, well, if this is a multinomial with some parameters, I can put the prior over those parameters, right? And if this is a transition matrix has some parameters, I can put the prior over their parameters. So in many cases, there's a lot of work that looks at HMMs and attempts to put priors that induce sparsity or anything of that sort, right? So in this case, P of m could be Dirichlet because your mu's have to lie in the simplex, because typically they have to sum up to 1 if you're modeling multinomial variables. You can also do things like sharing the prior. This is also commonly done, which is all of these different random variables or parameters of the distributions are going to be shared, right? So you can sort of specify it this way. There's only one common prior, and now you're getting into these hierarchies, right? You can have a prior that's shared across all of these different conditional probabilities. The other thing that you frequently see is the notion of parameterized models to control the exponential growth. It's sort of trivial, but let's look at it. Suppose I have x1 up to xm as being discrete, each of which takes k states, right? And let's say I want to model the conditional probability of y taking value 1 given all of these x1 up to xm. Right? If I want this particular probability distribution to model to be as complex as I want, then it will require k to the m parameters, right? Because I have to specify k to the m numbers. I can say, well, what's the conditional probability that y taking value is 1 if the first x1 takes value 1, x2 takes value 1, x3 takes value 2, x4 takes value 5. Right? What is that number? And I could have to go through all of these different combinations to come up with arbitrary distribution that I want. But we can have more sort of constrained representation of the conditional probability by using logistic function acting as a linear combination of the parent variables. So I can say, well, in fact, the conditional probability is going to be guided by just take the weighted average of my axis and pass it through the sigmoid function. That should be very familiar to you as logistic regression, right? And you can see that now dependence on parameters is becoming linear in M, right? Now, obviously, this is a much more constrained version of specifying this conditional probability, right? And so it's much simpler. So it cannot model complex distributions. If my y really depends on some weird combination of axes that really gives me y1 and nothing else, then this model is not going to be able to solve it, right? It's mostly if your classes are linearly separable, it will be able to solve it. But if it's not linearly separable, just as we've seen with neural networks, this representation is not going to solve it. Whereas this representation could solve it, but it requires exponential number of parameters. So this is a restricted form of the conditional probabilities, but it requires only m plus 1 parameters and it's linear. Let's look at the linear Gaussian models. And these are actually heavily used in practice. And once we start looking at the variational autoencoders, we're going to be making use of these kinds of models. So far we've looked at discrete random variables, right? Let's look at multivariate Gaussian distributions and see that the multivariate Gaussian distribution can be expressed as a directed graph corresponding to the linear Gaussian model. So let's look at it. So let's say we have an arbitrary acyclic graph over d random variables in which each node represents a single continuous Gaussian distribution with mean given by a linear combination of the parents. So here's what I'm going to say is I'm going to say the distribution of xa, I can just put it here, the distribution of xi conditioned on the parents in my graph is going to be given by, I take a weighted average of my parents plus some bias term, that's going to be my mean, and then there's going to be variance. Okay? Does that make sense? Very simple model. Take the weighted average of my parents, that's my mean, I add some noise to it. Wij and bi, the parameters governing the mean, and vi is the variance. Okay? Oops, sorry. And the vi is the variance. So now the log, like if I look at this particular problem, the log of the joint distribution will take this form, right? And let's look at this particular form. In this particular form, I have a bunch of conditionals, right? Because my whole graphical model decomposes into conditionals. And what does this conditional look like? Because this is a Gaussian model, this conditional basically says it's 1 over vi, this stuff squared, plus some constant terms. Okay? Now, when you look at this representation, what does it tell you? Somehow it should be telling you that this whole thing is a Gaussian, right? So anytime you have bunch of sort of like squares, so let me just shut it down. Every time you have bunch of squared terms summing up together, you have to sniff Gauss in there somewhere, right? Maybe you can do something, put things terms together, and it's like you just have Gaussian. And Gaussians are very easy to deal with. So the constant here doesn't depend. So this is a quadratic function of x and has the joint distribution as a multivariate Gaussian. In fact, you can compute what this multivariate Gaussian is. So for example, let's look at the directed graph over 3 random variables, x1, x2, x3. And all of them are being Gaussians. Then I can determine the mean and covariance of the joint distributions. Let's go through this exercise very quickly. This is my conditional probability. It just has a Gaussian form. Depending on my parents, I take a weighted average. So xi can be written this way. Xi can be written as the weighted average of the parents plus square root of the variance, the standard deviation, times epsilon, where epsilon is normally distributed with 0, 1. With mean 0, variance 1, right? Any Gaussian random variable can be decomposed into the mean plus standard deviation times normal 0, 1, right? You guys are familiar with that. That's essentially how, when you draw a random variable from arbitrary Gaussian, you first draw a random variable from 0, 1, or 0 identity, and then you multiply it by standard deviation, you add the mean, and then you have a draw from a multivariate Gaussian. Right? So the expected value of this random variable, is just going to be the sum of the expected value of xj's, which are the parents, who are the parents of this node, right? Because expectation, you can push it inside the summation. So now we can find components of xa, right? It's going to be expected value of x1 all the way up to expected value of xd by doing pass, central pass. You start at the top and you proceed in order, right? So you figure out what's the expected value of x1, expected value of x2, expected value of x3. These are the expectations. So that's going to be the mean of the multivariate Gaussian, right? And then you can do the same thing for the variance. If I'm looking at the covariance between xi, xj, I'm just opening it up. This is the definition of xj, right? Depends on its parents. You can just do a little bit of algebra, but I promise you it's going to turn into the covariance between xi and xk, where xk is the parent, plus this noise. Okay? So now I can compute the covariance between any 2 points. So the whole thing is just a multivariate Gaussian with mean, with an individual covariance entries given by this expression. So let's look at the 2 cases. Let's say there are no links in the graph. So the graph is fully factorized, right? So all the wij's are going to be set to 0, right? If it's a fully factorized graph, because there is no connection between any 2 nodes. In this case, the expected value are just going to be the biases, right? If I go back here, let me just go back quickly. If I look at this term, and if wij's are 0, then the expected value of each individual node is just going to be the biases. And the covariance is just going to be v1 up to vd, so it's diagonal. So the joint distribution represents d-independent univariate Gaussian distributions, right? So it's going to be a fully, a Gaussian model with mean given by the bias terms, BIs, and covariance is a diagonal covariance matrix with individual variances, right? And that's exactly what a fully factorized distribution would look like, right? On the other hand, if the graph is fully connected, everything is connected to everything, then the total number of parameters is going to be d squared over 2 for the covariance and d for the mean. And this is divided by 2 because the covariance corresponds, it has to be symmetric, right? So that's why you're dividing by 2. But this basically specifies a full Gaussian distribution over d random variables, right? That's how many parameters you need to specify the Gaussian distribution. So when you think about Markov chains and you think about Gaussians, each conditional is given by Gaussian, then basically the whole model is a Gaussian distribution, right? Does that make sense? That's why you don't really see models where I have like 3 layers of latent variables and all of them are Gaussians and everything conditionally is Gaussian. Because if you do that, the whole model is just going to be one big gigantic Gaussian. You can marginalize the hidden variables that would just correspond to a specific covariance structure, right? So in order to have something that goes beyond Gaussian, you need to add some nonlinearities or sigmoids or something beyond that. Otherwise, the full system is just going to be a Gaussian. Let me show you another example. This is an example of a bilinear Gaussian model. So it's bilinear, so it's no longer Gaussian, but these models are heavily used in recommended systems. Consider the following model. Before I do that, you're trying to solve this problem. You have users, you have items. Some users specified ratings, but for some of them you don't know what the ratings are, and you're trying to guesstimate what these ratings are. Okay? So let me look at the following bilinear model. I can say, well, here's my user preference. It's going to be sampled from some Gaussian. Here's my item preference. It's going to be sampled from some Gaussian. And the way I'm going to get the rating, let's say it's a real valued rating, is by taking a dot product between these two vectors. Right? So it should be U transpose V, or in this case, if it's, it's just U times V. But if this is a vector, then this is going to be dot product between the two vectors. So the reason why it's called bilinear is because you don't know U and V. Right? If you think about regression models, in regression models, you typically know one of them. So V, if you know V, you don't know U, and you're trying to model R, then it's a regression problem. Right? Because you can do least squared to figure out what that is. Here you don't know both of them. So that's why it's called bilinear. Both of them are Gaussian terms. And the mean is given by the product of two Gaussians. And so now you can be in this situation where you can say, well, here's user 1. And user 1 rated these 2 items. Well, user 2 only rated this item, but I'm trying to infer preference of the user 2 for this item. And, this particular item was rated by user 1, so you have to observe the rating, right? So you construct this kind of a graphical model like this one, and you have some unobserved elements, and these are also unobserved because you don't know what the preferences are. So based on observed rating patterns, you're trying to infer the states of these new ratings. And this is what the bilinear model would look like. For each user, you draw from a Gaussian. From each item, you draw from the Gaussian. And then you're modeling your rating patterns as a dot product between user items and user preferences and item preferences. This is known as a basic instance of matrix factorization or probabilistic matrix factorization model. It's very simple to fit, but it has this particular graphical model. Right? So you have users, you have items. Once you draw Gaussians from them, you figure out what the ratings are. Right? And how you do inference is that you clamp these variables to the observed values, and then you're trying to infer preferences of users and items. Okay? So if you think about these kinds of models, these directed graphical models, in hierarchical and Bayesian land, you have some data, you have some priors, you have some hyperpriors. This is an example of matrix factorization model where, again, you have some priors of users and items. You don't know what they are. You're trying to infer them from the data. You have some hyperpriors and you have hyperpriors. So you can start building hierarchies that way, right? It's a very commonly used technique. Conditional independence. Let's look quickly at the conditional independence properties, and I'll go through it fairly quickly, just so that it's probably for many of you it's going to be fairly easy. A is independent of B given C, if we have this equation, right? So A and B are independent, which basically I can say I can drop B. Equivalently, I can say if A is independent of B, then I can write this probability as the product of these conditionals, right? So the joint can be written as conditional of A given C times B given C, right? That basically what the meaning is. A is independent of B given C. And we'll use this notation. A is independent of B given C. An important property of these graphical models is that these conditional independence properties of the joint distribution, you can read them directly from the graph without using any sort of analytical manipulation. So you can look at the graph and you know what's conditionally independent of what. And this is a general framework for achieving this. It's called D-separation, which stands for directed separation. That was done by Judah Pearl back in '88. And I think he also got Turing Award for this work. So it's, it paved a way to come up a whole bunch of different graphical models and examine conditional independence properties, right? So for example, here's an example of the conditional independence provided by the concept of IID distributed data. So in this particular case, let's say I condition on mu. If I condition on mu, then this data set decomposes, right? Given mu, all of these things become independent, right? But if I integrate mu out, or if I don't condition on mu, then all of these entries become dependent. So it kind of has the fact of the way that if you have a latent variable, if you condition on latent variable, your observations become independent. But if I sum out or integrate out these latent variables, then all the, all of your data points become dependent. Right? And that's what you want when you're modeling the data. And this is known as a Markov blanket. And this is going to be important when you're doing inference in these models. The Markov blanket of a node is the minimal set of nodes that must be observed to make this node independent of all the other nodes. Right? Why is this important? So here's an example of a graphical model where my Markov blanket would include parents, co-parents, and children. So if I have another node here that's connecting into this node, then this node here is going to be independent of this node, conditioned on these states, or conditioned on these random variables. Right? So why is this important? Why do we need this? Any guesses? So we really need this, and we'll see later in the class, we need these properties in order to do inference. In particular, we can do inference in parallel, because in order to infer the state of this random variable, I only need to know the states of its Markov blanket. Imagine I have a graph with thousands of variables, and it's a complicated graph, right? If the state of this variable would depend on everything in my graph, then the problem would be very hard to solve. But if only depends on my local Markov blanket around me, my neighbors, then I can just look at my neighbors and do inference about this node. And if I some node somewhere else in the graph, I'll look at its neighbors and do inference for that particular node. So one thing I can do is I can run it in parallel. And it will form the basis for inference using a Markov chain or belief propagation algorithm, because everything that I need to infer about a particular state will just really depend on my neighbors. And how you define neighbors? You define it as all the parents, all the children, and the co-parents. And And you can really do it by just looking at the joint probability distribution, writing it as a bunch of conditionals depending on the parents. And you can see that, just by definition of this conditional probability, factors that independent of xi will cancel between numerator and denominator, and that brings you to this conditional probability and the definition of the Markov blanket. Right? Question for you. We have a few minutes, but I wanted to get this point across. There is something known as explaining away. How many of you know what explaining away is? A few, not that many. Let me just look at this graph. And let's look at this particular node. Why there is a dependency between these two nodes? Why the state of this node will be impacted by the state of this other node? Or why is this thing will depend on, this thing obviously depends on both. But if I want to infer this state, why does it matter that, I know the value of this state? Yes?
Well, let's say the relationship of these two parents are x plus y, and the children is x plus y. If you y, the new y is y plus 1, then the new x must be x minus 1.
Sure. Let me explain it in a little bit of high-level terms. This is known as explaining away. Explaining away because you're introducing dependencies between these two. Let me see if I can come up with an example. Suppose this node represents the grade that you get in this class. Okay? I pick a student, and that represents the grade that the student gets in this class. Okay? Now, there are two factors that can be impacting the grade. One factor is, let's say here, a student is not really paying attention, not doing the homework, and so you get the grade. Or the student is really doing the homework and is, doing everything, and that impacts the grade. That's one factor, right? Depending how much you work. And the second factor is maybe is an instructor effect, right? Let's say you have an instructor that kind of mumbles and drives all over the place and completely not very good at explaining things. And so in this case, regardless of whether the student is hardworking or not hardworking, maybe you end up getting a bad grade because the instructor just can't explain things. Or the instructor can explain things quite well, and then that can have an impact. Right? So imagine that a student gets a bad grade. Which one you think causes it? Okay? Well, if you get a bad grade and you look at the instructor and the instructor is just all over the place, not explaining anything coherently, what would you infer about the student? It can directly impact the student, right? Because the student can say, well, I've been working hard. It's just the instructor is not really explaining things well. Or the other way around. If the fact that the instructor is doing a really good job at explaining, but you still see a bad grade, that directly impacts the state of this variable, right? It directly saying that the student is not really doing a work, right? So you can see that depending on this state, it can impact this state. In fact, this particular example was developed by Judea Pearl in '88, and he lives in California, and a lot of earthquakes in California. So he had a cool example where he said, look, suppose you're in your house, and your house jumps. Okay? Now, there could be two explanations. One explanation, there is an earthquake. The other explanation is that a truck hits your house. Because your house is near the road, and once in a while, cars run into your, hit your house. Okay? So now, you see your house jumps, you turn on TV, and the TV says there is an earthquake. Okay? So the fact that there is an earthquake and your house is jumping, does it impact the probability of a truck hitting your house? You're going to say, no, truck didn't hit my house, right? Obviously, because you know that the earthquake already explains that your house is jumping. On the other hand, if the TV says there is no earthquake, you know the truck hit your house, right? So the probability of the truck hitting your house. So it really depends That's why you have this explaining away. You have really codependence that impact what you're observing. Right? That's why you not just need to observe what this is here, but you also need to observe the state of this variable, because it can explain what's happening here. Right? So that's a very crucial concept known as explaining away, that basically makes it difficult for these directed graphical models to do inference in graphical models. Because if you observe something, you don't know, is it caused by this thing or by this thing? Depending on the state of this thing, maybe this thing is already explaining what you see, so this thing can, explain something else. So directed graphs can be thought of as distribution filters. You can really think of them as you have some data, you pass it through the filter, so you have some distribution, you pass it through the filter and you get this sort of, only distributions that respect these conditional independence properties get passed through the filter. If it satisfies the factorization property, right? So the fully connected graphs exhibit no conditional independence properties. So if everything is connected to everything, then you can fit arbitrary distribution. That's not very interesting. In the fully disconnected graph, there is no links, corresponds to a joint distribution that factorizes over the product of the marginals. Right? So it's the simplest possible distribution. And popular models, when we look at directed graphs and directed graphical models, are, some of the popular models are topic-based models. These are latent Dirichlet allocation models. So for those of you who've seen these before, this is nothing more than just a deep directed graphical model. You have some prior, the distribution of topics, you specify distribution of words, and then you get to observe word counts and so forth. Right? Bayesian probabilistic matrix factorization, if you're doing recommendation-based systems, or you have some sparse matrix, you're trying to fill in the entries of the sparse matrix. You have Bayesian probabilistic matrix factorization model. It kind of has this bi-Gaussian representation of it, and you can stitch them together, right? So these are some examples of fairly popular directed graphical models, right? Later on in the class, we're going to be seeing models, deep generative models, such as Helmholtz machines or variational autoencoders, where you have some prior, which could be a Gaussian, and then you pass it through nonlinearity, and then you get another layer, which is again stochastic layer, a bunch of random variables. You pass it down, and then you get to observe your data, right? And so, again, you can think of them as instances of these kinds of models. It's all about what kind of conditional distributions you specify and how you specify them. Okay, I'm going to stop here. So what we're going to do in the next class, we're going to look at the undirected graphs, and then we're going to start looking at restricted Boltzmann machines, deep Boltzmann machines, and deep belief networks. There is a reading material for these directed graphical models. Make sure that you are familiar with these models and you understand how you're constructing what is explaining away, what are the conditional independence properties for these models.